Welcome to the Punny Math Teacher. So we are going to do a two-pager today. So FYI, it's going to be a little long. I apologize sincerely. So expectations, make sure you're using twice this video's length to take notes, to wonder. Actually, this first page might go a little quick. So let's get into it. Remember, I have extra resources on my site. And our objective is to complete this one. So you started it last lesson with knowing what a relation is. Now we're going to go over functions specifically, and then you can be able to tell the difference between the two and compare and contrast. So let's go. All right. So functions, it is a two-pager. So if you want to label both pages, you can, or you can label it as just 23 and then just have a blank page after that and know that the next one's 24. So either way, you can find functions really fast in your notes, and that's the goal, is be able to find, okay, I'm lost on this concept, and then go find the page. So it's not about labeling every single page, it's about knowing how to find your notes within 10 seconds. That's our goal. 10 seconds, it's a good goal, you think? All right, so we're going to define the word function, because you're dying to know what it is, right? Okay, so a function is a relation. Shocker! But this is a special relation where each x has one y. All right, so this is a special kind of relation. Just like all squares are rectangles, all functions are relations. But not every relation is a function, and not every rectangle is a square. All right, so you've seen something like this before with squares and rectangles. We're going to do it again with functions. Just an FYI, I'm going to make a 4 square. So 4 squares, and then the bottom I'm going to write some. All right, so that's where we're headed with this paper. So I'm going to have an example column and a non-example column. Whoosh, and cut it in half. Okay. So I have a 4 square, and then I've left some space at the bottom to be blank. So an example of a function, I'm going to draw a mapping, and I'm actually going to draw it with, why not? We'll do a calligraphy pen, because it's fun. We'll see if this is thin enough. It may not be. Okay, so I'm going to have 1, 2, 3. This is really dried out, but okay. 4. Ooh. Okay, and I'm going to draw, okay, UMAP, UMAP, UMAP. And I want to throw that away. I do not like the texture of that one. Oh, it's chalkboard. Okay, so 1 is an X. Domain always goes on your left. Range always goes on your right. So 1 is an X, and it maps to a 4. So it maps to only 1 Y, which is awesome. 2 maps to 1 Y, which is a 5. 3 maps to 1 Y, which is a 4. That's why this is a function. It matches to only 1 Y. A non-example of a mapping would be if I had, okay, 1, 2, 3, 4, and 5. 1 is going to map. 2 is going to map. 3 is going to map. All right, so notice here, the 1 maps to 4 and to 5. So it maps to 2 outputs, or 2 Y values in the range. 2 maps to 1, 4, which is good. 3 maps to 5, which is good. But that 1 breaks it. That's why it's a non-example. That is just a relation. Both of these are relations, but only the example is a function. Okay, what if I had a table 1, 3, negative 1, 2, negative 5, 12. Okay. This is still a function, but if I change it to this and I add an extra point, notice how 1 maps to just 3. Negative 1 maps to just 2. Negative 5 maps to just 12. That's okay. And even if I add 2, 2, even though they use the same Y value, that's okay. Negative 1 is only mapping to 1 Y value. 2 is only mapping to 1 Y value. They could be the same as long as it's only one they map to. The non-examples issue is -1's mapping to a 3 and to a 4. I don't know if I input a -1, I don't know what I'm going to get out. Am I going to get a 3? Am I going to get a 4? You can't have both. You got to have only one for a function because you got to take an input and get out an output. All right. So, and then graph. I knew there was one more. Graph. Graph. Okay, I'm going to sketch the axes, so I'm actually going to graph it with a different color. Okay. This is a function. Okay? Each x, this x value has only one output, one vertical motion. This x value has one vertical motion. This x value has one vertical motion. Yet this x value has two vertical motions. It's going to hit at two spots. That is not right. That means it is not a function. These other two coordinates, hunky-dory, perfectly fine. It's the other two that are, these two that make it and broke it. So it's not a function anymore. If I took off one of them, it's a function. Took off this one, it's a function. But because there are two of them, there are two outputs for the same input on x, that's what makes it not a function and breaks it. So the reasons, for example, so make sure each input has one output, okay? So another way of expressing that in a mapping, there is one arrow from each number in the domain. For a table way of expressing that is each x is only written once. I mean, you could write it technically again, but it's just repeating information. So I could write 1, 3 again, but that's just repeating information. And then with a graph, it passes the vertical line test, which I know you don't understand it now or like know what that definition is. We've gone over it, but you didn't really know what it was called at the time. That's what this bottom part is going to be over, is the vertical line test. So don't worry, we're going to get there. Okay, so each input has one output. So each input has more than one output. So for example, in this one outputs to 4 and 5. That's an issue. On my table, -1 outputted to 3 and to 4. That's an issue. And then my last one, I label that. Again, -1, sure, it goes out to like 2 and 4. I don't know, I'm just making that up. Here we go. 1, 2, 3, 4. There we go. Now it outputs to 2 and 4. So those output 2 times, and that's not what we want. For a function, it must be only 1. It can be nothing. Like -2 out here, outputs to nothing. That's okay. It can be nothing, but it can't be more than 1. And that leads us into the vertical line test. Vertical line test. If a vertical line intersects the graph more than once, more than one time, then the relation is not a function. And I'm going to write 3 examples down here. We're going to go through them all, okay? So sketch 3 sets of axes, and I'm going to draw a graph on them. Okay, So if you have a pencil or a highlighter or something that is going to be straight, this is our vertical line. So I'm going to take a vertical line, I'm going to drag it through my graph, going just from left to right. As I cross my graph, how many times is my brown marker intersecting my graph? One time. It could be none, which technically this goes forever, so it's intersecting everywhere once, but it's only intersecting once. This is a function. It passes the vertical line test. When I go through the circle, it hits once there, and now it hits twice. And then it hits once again, but it doesn't matter about those one times because those 2 times broke it. This is not a function. It is only a relation. It's a relation between x and y, which is awesome, but it's not a function. I can't put in one number and know exactly what I'm going to get out. And then over here, it's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh, 3. Man, this vertical line right here is going to mess us up, so this is not a function. If I chopped off that half the graph, though, boom, it'd be a function, no problem. But this little squiggle means it's a relation. So all 3 of these are relations. This one is only a function, so it's a special relation. We're going to move on to page 24. 11 minutes on one page. We can get it. We can do it. I got 10 minutes. We're going to get this under 20. That's our goal. So we are going to have 2 kinds of graphs. We're going to have a graph that is discrete, and we're going to have a graph that is continuous. So notice discrete, this is spelled differently than the English discrete. In English class, when you talk about someone being discrete and like quiet or hidden or shy or just like being hidden, I guess hidden, it's E-E-T. In math, it's E-T-E because it means countable. So discrete means countable. I have 1 pen, I have 2 pens, I have 3 pens. Those are countable objects. So when I graph a discrete graph, it's going to be countable points. That's 4 points. I can see that. They're not connected, they're just the ordered pairs. Continuous is uncountable, is one way to write it, because I could be 1.55 meters high, or I could be 1.556 meters high, or it could be 1.235 meters high. Like, with decimals, you can be anywhere in between. There's an infinite number of possibilities of height that people can be. So if it's uncountable, we're going to have a bunch of points all put together to follow a pattern. But if you have a bunch of points like that, in essence, it's a line. So if it's continuous, you'll be drawing a line for the function. If it's discrete, you're just putting ordered pairs and not connecting them. All right? So there are infinitely many dots that make up this line. You can't see them. You saw some of what I put, but you can't see them. They're all connected. They're all so close that they look like they're connected. Okay, so if I wanted to actually graph this, so we are going to graph with, it's called function notation. So I know this is a function, all right, and actually I'm going to set up everything and then I'll annotate it with a different color. F of x is the same thing as y, all right? There you go. Now you can see what I'm doing. All right, so we're going to come to solutions and not solutions at the end, but I do want to graph and just annotate some stuff first. So on this function, the x is my input. The f of x, that's how we say it, is f of x, is going to be my output. All right, so if our x values we're going to use are -2 is our first one. So if I'm going to plug in or substitute in -2, wherever I see an x, I'm going to replace it with a 2. So this is now f of -2 equals 2. I'm going to multiply because this is 2 times x, but I'm going to replace the x with a -2 and then put -3. 2 times -2 is -4, -3 is negative 7. So my y value would be negative 7. That's going to go on my y-axis. So the coordinate you could write for this would be negative 2, positive 7. If I go left 2 and go negative 7 and go down 7. 1, 2, 3, 4, 5, 6, 7. Left 2, down 7. That's my first coordinate. All right, what if I plug in or substitute in negative 1? So wherever I see an x, I'm going to replace it with a negative 1. That's negative 2 minus 3 is negative 5. So my coordinate is negative 1, comma negative 5. I'm going to go left 1, go down 5. All right, I want you to do the next one at 0, and then do the next one at 2. Pause the video. So f of 0, you should have plugged in that. When it's f of 2, you should replace the x with 2. 0 is negative 3. 4 minus 2 is 2. So the coordinate here is a y-intercept of 0, negative 3. And why is it called a y-intercept again? Because it intercepts the y-axis. It crosses the y-axis. It's caught the football, so the y intercepted the football. It's even in brown. All right, and then 2, 2. 1, 2, 1, 2. And I know with hand sketching, it's going to look a little off, so definitely try to having a regular slope and everything. And then I'm just going to take a random piece of paper, and I'm going to line up with as many of my points as possible. Ooh, okay, my scale is obviously not great. So this should have crossed exactly on all of my points, but this is human error. I am not perfect with how I drew my scale. And this is continuous. This is continuous. I'm going to write this. Continuous, because you could substitute any and all numbers into f of x. I could have plugged in negative 1.3. I could have plugged in 5.6. Like, none of those would have gotten me an error. It's a pattern. It's any number I plug in, multiply it by 2 or double it, and take away 3. That pattern is any point on this line. And we can see that by looking at solutions. So solutions are all points on the line. Not solutions are points not on the line. I'm going to have to do that, okay? So a solution, an example of one of those would be, we'll do negative 1, negative 5. So if I have f of x equals 2x minus 3. If my output is negative 5 and my input was negative 1, is the left-hand side equal to the right-hand side? Yeah. Negative 5 equals negative 5. That's a solution. If it gives you a true statement, then it is a solution. But what if I picked this point over here, just randomly? I want to test negative 2, 0. So f of x equals 2x minus 3. My output's 0. My input gets replaced with negative 2. So does 0 equal negative 7? No, this is not true. So negative 2, 0 is not a solution to this equation. It will not make it true. Whereas, I need to put this up here. Negative 1, negative 5 will be a solution and make that equation true. So that's how you know solutions are all the numbers on the line, because they make the equation true. And we're going to beat the 20 minutes. Woohoo! All right. There's your comprehension questions. I already went over them again. Pause it, do it. Have a great day.